We've talked about Riemann sums. And Riemann sum says, if I want to approximate what's happening to this function in terms of the area under the curve from some starting point to some ending point, we can break the curve up and say, look, each little part looks like a rectangle. Find the area of each part and add it up, and life is good. Well, that's an approximation. We want to do better than just approximating the area. We want to say the area is exactly this. So it's time for us to talk about finding the area. And no surprise, when we think about the process, well, what do we do with the rectangles? Smaller and smaller. Whenever you hear words or phrases that say closer and closer, smaller and smaller, bigger and bigger, limits are involved. So we're really going to be talking about limits, and what does that mean? Well, let's begin. So our starting point are the Riemann sums. And remember, how does it work? Well, we're adding up, and that's what the sigma notation represents. It's adding up a bunch of small individual rectangles. So in particular, we're going to split it up into some number, let's say n rectangles. So that's what this indicates here. Starting from the first rectangle to the nth rectangle. And each rectangle, there's a height, which is the value of the function inside one of these little pieces, and the width, which is the width of each little segment. So say, okay, height, width, area, add them up, life is good. So, of course, better and better approximations means what? We want to let the number of rectangles get large. Technically what we want is to say, look, each rectangle is a very good approximation. Now, the way we can guarantee good approximation is to say that the height is going to be pretty accurate. In other words, the height won't change much, because the more that the height can vary over the top, so if I have my a sub I minus 1 to a sub I, and I say, well, if the height can vary upstairs, well, the approximation will be off significantly. But if the height can just barely change at all, great approximation. So what we really want is to say we want the widths to be small, going to 0. Well, if each individual rectangle has a small width, it means there has to be a lot of rectangles. So intuitively what we'll say, all right, well look, what we're going to have is we're going to have the number of rectangles get larger and larger. So there's this idea of a limit. So we're going to say, okay, we'll have the number of rectangles n go to infinity. And we'll say, for convenience, we'll make each rectangle the same width. Well, what's the width? It's b minus a, that's the total length from start to stop, divide by n, the number of pieces we're splitting into. So there's our width, and if we use our right endpoint, we might as well. We have to pick, right? Then what we have is what? Our xk is this expression. Now, you might be saying, where is that coming from? So the way you can read this is really saying it's a plus delta k, where delta k, well, notice really, look, all the delta k's are the same, so it's just delta. So what we really have is, if you think of a0, a1, a2, and so forth and so on, then when we're talking about a plus, however wide the interval is, times k. So when k equals 1, that's our first interval, it says start at a, and this is a, and then go one step, you'll end up at a sub 1. So that's a plus delta times 1. When k equals 2, well, okay, so we want to go 2 delta. So that says we want to go the width of 2 rectangles. We'll end up at a sub 2. When k equals 3, if I add 3 delta to a, that says I'll get over here to a sub 3. So really, that's just saying that's the format for where the right endpoint will always be. So now we have our idea. Put it all together. Our width, there's our delta, k. Our height, our function, a plus b minus a over n to the k, great. add them up, and of course when n is large, it's a great approximation. For even better approximations, you let n go to infinity, and that will be the answer. Well, maybe, right? There's, of course, the question. So, what's the concern? Does the limit exist? So when the limit exists, then we are indeed finding the total area, of course, in quotes, area, from A to B. And we say it's integrable. So when you talk about saying, oh, this is integrable, it means, oh, we can find the area under the curve. All right, well, what's true? Well, it turns out that most of the functions we're going to look at are integrable. So if you're continuous, we can integrate you. You are integrable. Or if you're continuous except for some jump discontinuity. So a jump discontinuity, remember, you're like coming along and then boop, and you go along, boop. So as long as you have only a finite number of jump discontinuities, you're integrable. So in other words, the functions that we're used to working with most of the time are integrable. Okay, so how do we write this? Well, instead of writing it this way, and the limit as n goes to infinity, sum I equals 1 to n of fxi delta I, we write it in this notation. So let's make sure we understand what this says. First off, we've seen pieces of this before. We saw, when we talked about antiderivatives, we saw something called the indefinite integral. Well, this is called the definite integral. So this is the definite integral of f of x from a to b. So that's how you would read this. And, okay, great. Now, let's see what we have. This symbol here, that's the integral sign, but you should think of it as what? You took an s, and then you stretched it up and down. So it's stretch that s. Now why s? S for sum. Integration is really about adding pieces together. So what we want to do is emphasize that, oh, hey, integration is really about adding things up. Now, some other things is, okay, when you talk about a to b, we suppress notation here. What we really mean is from x equals a to x equals b. In other words, it's a start and a stop. In context, we can always figure out what the variable is being referred to. It's actually stored in this dx. Okay, so we're told, okay, x equals a to x equals b. Now, let's just pause and just emphasize. Sometimes it feels like, do I really need the dx? It seems kind of excessive to include it there. Do I have to? Yes, you have to. It's important. It's really, really important. And it might not feel important right now, but it will be important later on you go. Because one thing is it tells us what the variable is. See, this is saying x is the thing that's varying. You want to keep track of that. You might think, well, it's easy to do right now, but that's because we're in single variable calculus. Later on, we'll get into what's called multivariable calculus. And so we want to be sure our notation habits are formed now so that when it matters, we're ready. We want to be ready. So that it's really important to keep the dx. The other thing is the dx represents something. So how do I look at this? So one way you can think about this is really, you can say, look, I'm adding up, because integration is about adding up. So adding up, that's the integral sign, from starting at A and ending at B, right? And that's from these parts. So that tells me what I'm doing. So I'm adding up. That tells me where I start adding, tells me where I stop adding, and then it tells me what I add. And so we're adding up from starting at A and ending at B, and then it's our function, which we can think of as our height, and then it's our dx, which we can think of as our width. And so it's like, oh, I'm adding up little pieces of area, because that's what's happening over here. See, it's height times width. And indeed, you can tie all the pieces in together, right? The dx matches with the delta I, the fxi matches with the f of x, and of course, the sum. The sum part here in the sigma becomes the integral. So the pieces really correspond. So it's really intuitive if you remember integration is about adding things up. Now, we have talked about two kinds of integrals. Make sure you know what they are. The definite integral is going to produce a number. In other words, look, we're trying to find a total of something. So at the end of the output is the total. What is the total? It's something. Okay, what is it? An indefinite integral, on the other hand, is going to produce a function. It's the antiderivative. So it's going to have a very different flavor. And it's kind of interesting that we're putting these together. In fact, it sounds like they're really close to each other. We have the indefinite integral, you have the definite integral. Is there a connection? Great question. And we'll get to it. But for right now, what we want to show is actually, let's get our hands in there and do some definite integrals by doing some limit notation in some cases, some geometry in other cases, and say, hey, we can actually find the answers to at least some functions, and maybe that will give us insight into what's going on. Which sounds like we should go do some practice, because we should go do some practice. So hope to see you soon. Bye.